Yeah, I noticed in the first two talks there were no operators, right? So we will fix it today, right? So, and first, of course, I'd like to thank organizers for inviting me to this wonderful place, especially compared to Toronto in this time of the year. It's sunny and nice, at least today. Yeah, so it's a great pleasure to be here. And as you could see, my slightly modified title, shortened, I guess, it's going to be about the method that we currently developing. And the main motivation really is we would like to make some steps towards practical usefulness before error correction, right? So, and purposefully, I try to avoid, well, over-advertising this, saying that it's going to get us to a quantum advantage. I honestly thought about this a little bit recently that in principle, we may get to the usefulness, and I will define what usefulness is. It's probably still no an advantage. And since one of the questions was, how do you define advantage? For me, I'm coming from the quantum chemistry, and I'm interested in using quantum computing to advance quantum chemistry in challenging problems. For me, quantum advantage would be simply and concretely is the situation where we can take a quantum computer algorithm that is appropriate and maybe system-dependent algorithm, right? And being able to attack difficult problems for classical method more efficiently, time-wise. I don't even put the economic considerations for now because that tend to change with time and with the technology, harder even to predict. But maybe efficiently in time, we could deliver the accurate answer for the useful, clearly useful problems of quantum chemistry, right? So that would be beating classical methods in this quantum chemistry game. All right, now what I mean by usefulness is a little bit a less ambitious task, and it's more related to be still in the competition, okay? So there is a clearly competition in between quantum and classical, and I feel generally, maybe because I'm pretty competitive in general, right? So I feel like competition, it is very useful phenomena, and it helps to develop methods, right? Both quantum and classical. It's very productive way of improving things, right? Because classical methods learn what beats them if, let's say, somebody for the next time kind of says that, okay, well, in this problem, we can do something with the quantum computer more efficiently for this specific problem. Then the classical people usually go and see what structure could be exploited in the classical algorithms. So that, I think, in general, is very fruitful for classical development. And of course, quantum people, they are trying to learn from classical techniques and try to essentially improve their quantum algorithms as well. So that's what we will be doing in this method. That's the usefulness, essentially staying in the competition, right, and being the contenders. All right, so with that, let's see. There was also a question in the questionnaire about the history, about the NISQ, right? So this slide sort of probably summarizes my views that in quantum chemistry, back in 2016-17, when IBM published this Nature paper, I guess there were some hopes that VQE, the very simple algorithm, right? So everybody knows it, doesn't need an introduction, right? So it will help us to solve this challenging many-body problem for fermions, right? And the key idea here is why VQE had these hopes up that we can lower the circuit requirement. We can use the circuit to construct a fermionic wave function and then do the measurement instead of more complicated circuits that were required in QPE, right? And so that was the idea that was believed to get us closer to FIMOCO or some compounds which were challenging. With some error mitigation, that's clearly was recognized quite early, right? But essentially in this 2017 IBM paper, we have systems like Lithium H, Beryllium H2, some systems that you can do in seconds on a laptop, right? So clearly we were not that far in that quest for challenging systems. And honestly, the current situation is that we are not that far either, right? So we still can, I think the current record of doing VQE, honestly, is staying still within this like a lithium H, beryllium H2 systems, right? Maybe water, but there are lots of works where honestly there is a cheating going on because they don't optimize the circuits, right? So they just optimize things on a classical computer and just do the final maybe cycle of the VQE. Even that is quite challenging to go with for larger systems, right? So that's the situation right now still. And there are many problems of the VQE. You probably all know about them: measurement, optimization. But and my group worked on some of those. But we kind of came to realization that the number one killer of the potential hope, really, I would say, is the circuit depth, all right, without error correction. So the plot where error here is not necessarily hardware error, but the error, accumulated error, right? So you are trying to, you're very, let's say you don't care about your hardware, you just want to use quantum computing to reduce the error in the solution of Schrödinger equation, right? So that error. Right? And so let's say somebody came up with a circuit with the unitary transformations that take your initial state closer and closer to the eigenstate of the Hamiltonian. That's the blue part of that curve. You're very happy. You're reducing the overall error. But then eventually, because we have finite fidelities and they're not ones, right? So we have an exponential growth of the error because of that contribution, essentially, right? So we have this exponential wall, which honestly people don't put as a part of the VQE cost. But in reality, any VQE algorithm without error correction would have an exponential cost built in because of the hardware errors, okay, simply speaking. But let's say it's your lucky day, you're considering a simple system, and you could get the desired accuracy, chemical or not, kind of before the error from the hardware kills all your advantage, right? But in quantum chemistry in general, this is not serious because we would like a method that is scalable, right? So we would like a method that we can use for larger and larger systems. And if you increase your system size, then the curves will look more like this, right? So you will not reach the desired accuracy for larger systems unless your method somehow scales, I guess, logarithmically with the number of gates needed with the increase of the size, and there are no such methods. Yeah.
Artur, I'm a little confused about the first half of this graph where the error goes down in the number of operations for the first couple of.
Right. It's accumulated error, right? So let's say you start with a Hartree-Fock state or product state, right? And you're trying to find the eigenstate of the many-body Hamiltonian, right? So and you're using expectation value as a measure, right? So then, in principle, if you modify your product state with adding one unitary, optimize that unitary, let's say single qubit rotation or a bunch of CNOTs, so that overall the energy will go down. So you are coming closer and closer.
Yes.
Right?
Okay.
So that's what I meant. Accumulated error.
So
right?
the first half is just like
advantage of the using the ansatz essentially.
Yes.
Right.
Yeah.
So that you that gets you closer and closer to the result.
So you have this trade-off in accuracy of your ansatz versus the accuracy of your the error incurred from your operations having errors in them.
Eventually they will catch up with you, right? So
thank you.
So that to me is the essence of the main issue of VQE before the error correction, right? Okay, cool. All right, so the natural question, what do we do, right? So what are the alternatives? And the general idea, I guess, and what will help, I believe, in the NISQ or even in early fault-tolerant is to have more flexibility of shifting the load between the quantum and classical computers, right? So very simple idea that I believe we stopped earlier with the than we should have. With the VQE, because yes, QPE required long circuits, VQE required shorter circuits, but that's it. You end up with in VQE with one wave function, and you have one circuit, And that's it. So you cannot reduce the circuit because the complexity of the wave function is given, well, by nature, right? And you only have unitaries to use. And OK, you could play with the ansatz somewhat, but there is still kind of limitations of what unitaries can do. And the circuit cannot be shorter than a certain depth, right, let's say. So there is need for more flexibility, essentially. That's what I think is very natural idea and very important one to implement if we want something useful in the NISQ or even early fault tolerant, right? So how do we do it? Again, simple idea, simple answer to the simple question. Well, we just need to have more wave functions, right? So if we cannot do it with one because you run out of circuit depth, you need to have many. And that's a simple construction, which is linear combination of unitaries, where you have a sum product state. In quantum chemistry, it's very frequently used as a Hartree-Fock state, as a product state to start with. And then you essentially can think of these circuits, UK, applied to the Hartree-Fock as your basis functions in the expansion, right, with some coefficients. And the coefficients could be found on diagonalizing the Hamiltonian, right? So this is, for some of you, very natural and old idea of expanding the wave function in the some subspace created by these circuits, right? And we could, in this, what is nice about this framework, we could trade the circuit depth. Well, we could make circuits shorter, and the number of basis states then will grow because shorter circuits we'll need more of them to represent the true complexity of the wave function, right? And so this is a natural bridge between VQE, where we have one circuit, one function, and what in classical quantum chemistry we know as configuration interaction. That is just essentially representing a wave function as a linear combination of Slater determinants. There, you could also think of every Slater determinant as a unitary that applies to the Hartree-Fock. It's just that unitary doesn't require circuit. It's a very simple one. It's just excitation of certain orbitals, right? So that's what people usually use. And with this ansatz, in principle, we could be anywhere between these two limits, right? And engage quantum computer as much as we want, right? More powerful quantum computer will allow us to have longer circuits. Less powerful quantum computer will shift us towards more matrix elements, in principle, right? Yeah.
Maybe this okay, trying to understand this better. Maybe I'm trying to play devil's advocate.
Okay.
So I think you might have brought this up yesterday during Lex's talk.
Mm-hmm.
But when doing these, estimating multiple overlaps, there's then the need for generalized eigenvalue solver.
My next slides. Okay. So thank you.
So I was just going to ask if maybe this advantage that you get from having
maybe we'll lose it all, right?
Comes at the trade-off of getting more precise estimates, and it doesn't. Your error tolerance gets even smaller.
Right, so we don't want to introduce more measurement overhead. We don't want to use to introduce other bad things like maybe instabilities, condition number problems with this trade-off, right? So we would like to keep the situation that it's really sort of like it's described here, right? So, and of course you are pointing out very important problems, and that's what my next slide is about. This is not such a new idea. Since, I believe, 2017, Jared McLean proposed the subspace expansion method, where I will tell you in a moment the motivation was completely different, right? So 2017, people still believe that VQE can save the world, right? So, and Jared's idea was, okay, you use, instead of Hartree-Fock, VQE state for the ground state, right? And then these unitaries, they were used essentially to produce excited states, right? And so it wasn't about the circuit depth reduction. But then later, people were developing these ideas, and we heard also talks yesterday from Matthew and Lex, right? So essentially, there are plethora of methods that all could be under umbrella of subspace expansion. And they all have these features. In principle, you end up with generalized eigenvalue problem. Why? Because the unitaries that you put, they don't guarantee orthogonality. all right, between the states. And here, just to elaborate a little bit more on this, motivation initial one was excited states. Another motivation in some of these works was avoiding optimization problem, right? So some suggestions like this were made, just unitaries being Krylov, I believe Krylov Quantum Subspace Diagonalization methods, right? So this is not circuit reduction kind of motivation at all, right? Because this you would imagine very long circuits. And only in 2020, I believe, in work of Bill Huggins and Birgitta Wally, there were some early mentioning of the, okay, well, why don't we use this idea for circuit depth reduction? And I believe since then, people start considering this as a circuit depth reduction possibility. But even with that in mind, you still have this problem of measurement, which is now even worse, right? Because instead of one matrix element in VQE, you have a lot of matrix elements. Maybe not millions, but order of thousands easily, because yeah, you have system. Some of the part of the wave function is treated classically, right? So then, even in my opinion, worse problem, because it's really hard to control. It's a linear dependency buildup potential from non-orthogonality of states and condition number, which feeds back to the measurement of matrix elements, because if you have lower stability of the problem, the more accuracy is required for the matrix elements evaluation, right? And some of these proposals have really long circuit depths, right? So that's another problem with all these old subspace expansion methods, all right? Now, what we want, and I believe we somewhat achieved, let me just tell you a set of things which we would like to avoid in the normal subspace expansion. We would like to avoid orthogonal, or we would like to avoid overlaps. We would like to have orthogonal configurations, so no S matrix. We would like to avoid excessive measurements, so the matrix elements should be evaluated or measured on a quantum computer efficiently. And that I already mentioned, the whole idea of trading the number of gates with number of matrix elements, that is very essential. We would like to have that because that allows us to essentially adjust to whatever hardware can provide at the current moment. And then, in principle, this is desired but not necessary. It's well, it would be nice to not do the optimization because it's nonlinear optimization after all, and pre-compute amplitudes of our unitaries using classical methods, because after all, we can always compensate non-optimality of those unitaries by just putting more work on the finding the coefficients by solving eigenvalue problem, right? So those are the desired qualities, and this is essentially the outline of the rest of the talk. I'll tell you about choice of the basis states that allow us to achieve that. How do we reduce the measurements? I'll show some results on the systems that are larger than whatever was in an IBM paper for the VQE, right? But still relatively small, right? And I'll show some extension at the end that are possible for this algorithm and summarize. Okay, that's the plan. Oops. All right, now, great. So the key character or key component of our method will be this notion of quasi-symmetries. So what are these? Quasi-symmetries, they are like normal symmetries. Normal symmetries are simple operators that commute with Hamiltonian. Quasi-symmetries are simple operators, but they don't commute with the entire Hamiltonian. They commute only with the maybe big part of the Hamiltonian, but not with the entire thing, right? So, and we want to create basis states that are not necessarily, well, they will be eigenstates of the normal symmetries, but on top of that, we will make them ultrasymmetric. So we will make them also eigenstates of these quasi-symmetries. So simpler operators that not necessarily commute in the Hamiltonian. Okay. So what will this give us? It will give us orthogonality because we know from the early days when we learn quantum mechanics, or linear algebra really for that matter, right? So we know that any eigenvector of the Hermitian operator that has a different eigenvalues, they are orthogonal, right? And so enforcing that functions are coming from the eigen functions of the this symmetry of Hermitian operators, right? So they will be orthogonal by construction. Okay? And a little preview on how will we address measurement problem. You could see that the Hamiltonian matrix elements will, between the two basis states, will contain the Hamiltonian part that, let's say, commutes with the quasi-symmetries, and therefore that part doesn't really couple the wave functions or the basis states from different symmetry sectors. Okay? And there will be only some part of the Hamiltonian that couples these different states because that part is not commuting with our quasi-symmetries. Okay? So that's the origin of the reduction potentially. And I will elaborate on that later more. Right? So these are the two definite pluses of using this constrained quasi-symmetry eigenstate as a basis states. Right? There is another also big improvement, and that is that because we are imposing these quasi-symmetries on our states, the states may they will have less of the entanglement than they could potentially have in general, being general states in Hilbert space. And I want to illustrate that in the simple 4-qubit case. Right? Let's say we have a 4-qubit system. Right, and we don't worry about the true symmetries, number of electrons, blah blah blah. Right, so all that stuff. So let's say we have for the 4 qubits Hilbert space 16-dimensional. Right, so we have these coefficients. We have the Slater determinants. Every Slater determinant is just a binary string of zeros and ones. There is 16 of them, and you can obtain all of them from some sort of reference let's say 0, 0, 0 state, right? By doing some Clifford flipping, right? So of the qubits. So this is, you could think of it as a classical picture because you obtain these coefficients if you want this state to be an eigenstate of some 4-qubit Hamiltonian using like 16 by 16 diagonalization, right? And so, okay, so this is purely classical, great. Entanglement can be built here, but we need to diagonalize the matrix. Now, here's an illustration of these quasi-symmetries. Let's imagine we introduce these two operators. They now have Z1, Z2, and Z3, Z4. So they are kind of local. They only act on 2 qubits at a time, right? And what they do, they split the entire Hilbert space to the sectors, 4 sectors really. And to give you an example, let's say if we impose the condition that every of these symmetries is equal to 1, there are only 2 values, +1 and -1, right? So, but for 1, 1 sector, we have these 4 states. Other states are outside of this sector, right? And now we can rewrite our function as a linear combination of just 4 symmetrized states. Each of these symmetrized states could be thought as a linear combination of 4, like this 4, for example, or other 4s, right? And so these 4, let's say if we're considering the sector which is 1, 1, right, can be obtained by a shorter circuit because it just needs to rotate within this subspace, not within the entire space, right? So that is clearly reducing the circuit that we need to prepare the states that are under constraint that they should be eigenstates of some symmetry operators, okay, or quasi-symmetry operators. And then the idea here is that these D coefficients we obtain maybe classically by diagonalizing the Hamiltonian matrix, right? So my main point here, whenever we impose these local symmetries, we can partition the full exponentially large Hilbert space to sectors that we enumerate with the, well, symmetry labels essentially, right? Okay.
Will your S's always be polys?
No, not necessarily, but it's good to have them local, mutually commuting, and functionally independent. So yeah, for obvious reasons that you want to split the space into sectors, and there will be a part that comes from chemistry. Of course, if we just do this partitioning, we in principle, what we did is we split exponentially large problem to square root of the exponential, so still exponential problem on a quantum computer, and another exponential problem on a classical computer, right? So ideally, you want to find such symmetries where, well, not all the D's will be non-zero, right? So you want, in principle, to have these quasi-symmetries that would allow you to truncate this part and would essentially require fewer terms, not from all the sectors. Yeah.
And how do you do this in a way that the sector you choose has good overlap with the ground state?
Yeah, so that's the chemical part. That comes from the chemical intuition. At the end, I will show some of the algebraic ways we are exploring right now. And it's really a key one of the key questions, how to find those quasi-symmetries. But, and interestingly, algebraically, that hasn't been explored. But what was explored for a long time by chemists is these intuitive notions of which I will show come from the, well, just the early theories, Lewis structures, bond breaking, and some ideas of locality of the d orbitals in transition metals, right? So chemists knew for a long time, they just don't phrase it as like quasi-symmetries, but they knew about these operators, right? And they were using it in the classical methods. But now here in the quantum methods, you still can use them by essentially what these guys are doing to the unitary circuits. They are putting the constraints on what generators you could put here, right? So this generator should not break the symmetries. They should commute with them, right? Yeah.
You're probably going to tell me more in the next 20 minutes about this, but I worry that by enforcing so much symmetry, you sort of already mentioned this, but I'm going to ask it directly, that you collapse your circuit into in some extreme, it would just be a Clifford circuit, or a Slater-determined, or a more general Clifford circuit, or a Clifford plus T circuit with only 7 T's, right? Something that I could go classically simulated efficiently. And that would be fine, because I only care about getting the right answer. So if you do this and it collapses to like Clifford plus 27 T's and no more than 27 T's, and I can go use a really efficient Clifford plus T simulator to just do that short depth T, that would be awesome. But if I want to, your sort of byline was, or your tagline was useful quantum computing before error correction, then it starts to be a sort of very subtle issue.
Yeah. So, and to connect to your point, actually, one can say that in this case, in the CI case, our quasi-symmetries are occupation numbers. So they are single z's in the quantum qubit language, right? So if you're enforcing single z's as a symmetries, 4 of them, then your states will be just the product states, right? And you may end up with that if you are, not worried about, well, if you, I guess, search for symmetries and you kind of decide, okay, I am fine with that as long as the results are good. Or maybe my quantum computer will not be able to handle the circuit. So, but in principle, we know how to avoid this situation. We know, for example, from the algebra that, okay, if we at least put 2 z's, then the subspace we're working in is at least it's a 4-state subspace, and then these guys, they will create two double degenerate subspaces in which we rotate. Right?
Yeah. So I don't know exactly what these Z's are, but anyway, if you use a determinate space Jastro, which has Z1, Z2, now where my Z's are like Pauli matrices, which are very similar to, I think, what you're saying here, a determinate space Jastro only really sort of changes the phase, and like a CI expansion with a determinate space Jastro, the determinate space Jastro does nothing because you wouldn't optimize those parameters.
So you should not think about that. I will show you how this, I see what the problem you are referring to, but these guys are better than that. You will see in a moment why. All right, and then the final line here is just to show that VQE in principle in this picture would be not imposing any symmetries, then the whole state is unitary, but it's more complicated. It will be able to generate these 16 configurations, right? Okay, cool. Now, what are our quasi-symmetries, right? So that's one of the key questions. And in this work, and the part of the Q, what the method name is, QSense, right? So it stands from the seniority. So there is this concept in the quantum chemistry, seniority, and it can be clearly defined as an operator. The global seniority is a sum of orbital seniorities. That's essentially fermionic modes, right? And what these orbital seniorities are doing it's a simple occupation number operator, right? But what it does, it really counts the number of unpaired electrons, right? So if one orbital has 0 or 2 electrons, then the orbital seniority is 0. And if it's a projector, essentially. And if the number of unpaired electrons on the orbital is 1, then the orbital seniority will be 1, okay? So if you sum all the orbital seniorities, you get these global seniorities. This is the 0 seniority sector 2, and 4. They are only different by the number of unpaired electrons, essentially, right? One thing to realize right away is that this is just a different way to split exponentially large Hilbert space, right, in the many-body case. And even 0 seniority, if you it allows to have all the occupied orbitals in the Hartree-Fock to be unoccupied, and all these pairs go to the unoccupied orbitals, like here explained, right? So you, in principle, have now still exponential space of Slater determinants, okay? Even in the 0 seniority case, right? And then you have somewhat also exponential, but maybe slightly smaller spaces in the seniority 2 and 4. All right. So this is going to be our quasi-symmetries, and why it works, and why we're hopeful that this is a better split of the space. I'll show in a moment. All right. But another interesting fact about these seniorities is that if you look at the Hamiltonian, what parts of the Hamiltonian couple different seniority sectors. So interestingly, Hamiltonian split only to the 3 parts. So this guy only connects the same seniority. This one plus minus 2. This was plus minus 4 seniority sectors, right? So there's a clear split where you could sense that this will help us to reduce the number of measurements, because if the states are with a defined seniority, only some parts of the Hamiltonian will connect them. Yes.
Yeah. So can I understand this decompositions as you write your Hamiltonians into the frustration-free form?
Right. Yeah. Right. And now, yeah, for those who, especially, and me included, actually, being a quantum chemist, I always look down on all this old works of Hetler, London, like stuff that pre-Hartree-Fock, and even Hartree-Fock, even though it's useful theory, but we always learn that, okay, we need to use some sort of correlation methods in order to address the difficult problems, and all these early theories are kind of yeah, that's just were for general chemistry or something like that, right? But it turns out that for the first time I realized, okay, well, they are actually useful. So, and let's consider why. So there is this paradigmatic example of the bond breaking, right? So you start with a single bond, hydrogen, right, molecule. So you could describe it in the minimal basis as occupied, unoccupied, or bonding and anti-bonding orbitals. Comes from the linear combination of atomic orbitals. And if you stretch the bond, what happens is that bonding and anti-bonding, they become close in energy, right? And in order to describe dissociation, what you in principle need is just 2 configurations. In one, you have a pair on the occupied or on the bonding orbital, and in another, you have a pair on an anti-bonding, okay? And that's an alternative picture to completely equivalent picture that some of you may have in mind, and it is just unpairing electrons, right, on a localized orbital. So you could rotate orbitals and get equivalent picture where 2 configurations are 1 electron on the on one atom, like on one hydrogen, I label them A and B, and another electron on the other atom, right? So this is completely equivalent pictures, but this picture has pairs, and this one has unpaired electrons. So orbital rotation is essential to connect them, right? So because we know from the I guess experiment, like if you break multiple bonds, you will end up with the radicals, right? And even in hydrogen, you end up with the radicals in the localized picture. But you could always rotate it to the pair picture where you have pairs, in principle, at least for a single bond, okay? So that's the origin of why people thought that seniority is a good idea. Now, the downside is that the higher number of bonds, you are not be able to rotate all the unpaired electrons that you get in the separated picture into pairs, right? So just orbital rotations is not powerful enough unitary transformations to do that. So that's why even with orbital rotation, we need higher seniority sectors in principle, right? So this picture is not like we can describe every bond dissociation with zero seniority, but it sort of tells us that it's a pretty good picture to confine the orbital seniority sort of dissociation phenomena into the orbital seniority sector decomposition, right? Okay, so how good is it? Let's see, multiple bond dissociation, right? So this is from work of Scusieri and Henderson. So they study quite a bit the seniority in the classical algorithmic context. And what we see here is the stretch of 7 bonds in the linear H8 system. So it's quite challenging for classical methods. Electronic energy versus this bond length. They all equally dissociated, right? And this is Hartree-Fock. So mean field theory clearly gives a wrong dissociation limit, right? And the other curves correspond to 0 seniority only, 0 plus 2, 0 plus 2, 4. So you could see that 0 plus 2, 4 is already close to the full CI, right? And in this problem, up to the 8 is a full CI, right? So this is H8. And they have another system, nitrogen. So their situation is nitrogen is really challenging because you're breaking 3 bonds at the same time, right? And so what we have is essentially 0 seniority is qualitatively good, but still far from the full CI. But 0 to 4 curve is very close to the. Oh, actually 0 to 4 is a full CI kind of. It's a 0 2 is close, but yeah. So you could see that this seniority splitting is pretty good in describing dissociation even of multiple bonds. Okay, yeah.
How do you handle open shell systems where you might have an odd?
Yeah, so you just either use rotation to kind of represent them as pairs, and if that's not enough, you just add in more seniority sectors, right? So the ones which explicitly have unpaired. Okay.
So seniority 6 is what, 3 unpaired electrons?
No, actually 6 unpaired electrons. They go like you unpair pair and you get 2, 4, 6. Yeah.
Is it difficult to find the rotation that puts them in specific or seniority sectors?
No, you don't worry about the rotation. Well, rotation is optimized energetically, right? Okay, and you just allow. I will show in a moment. You allow the configuration, and then on top of that, you put orbital rotation, but not necessarily even on as a circuit, but as a rotation on the Hamiltonian, because it's easier that way. Okay, right? Yeah. Mm-hmm.
So when omega is 0, for example, then should I understand this as taking only a part of the terms, Hamiltonian terms, and diagonalizing?
No, the Hamiltonian is complete, right? But what you're taking as a 0 seniority, it's all Slater determinants where you excited all the pairs. It's a full CI, but without unpairing the electrons on orbitals, right? So this is still kind of expensive, right? But the hope here, and it's actually, we confirm that even though this looks like exponential problem, even in 0 seniority, but with unitary circuits, you could get with the polynomial number of generators, so the coverage of that space, essentially.
I think I saw in the previous slides you have you split H Hamiltonian to
Right, that's for measurement, right? So don't get confused with that. Here, of course, we are using the total Hamiltonian everywhere where we can or we need, right? And right. So okay, so let me get to the basis states that we use. They essentially start with Hartree-Fock and apply to unitaries. The 2 unitaries are the following. One is creating unpaired electrons for a particular basis state. We could use identity, so then all the electrons will be paired. And then the second, or we could unpair them, right? So, and then the second transformation is creating excitations in pairs. Okay, so this W essentially introduces these pair rotations, and the generators are selected so that they actually don't just change the phase, they actually rotate the pairs. So that conserves the seniority, right? But it introduces entanglement, right, by this. This also introduces entanglement because now we have a linear combination of unpaired Slater determinants, right? Seniority is preserved, and additionally, we of course preserve all the molecular symmetries because these are configuration state functions. They are S-square eigenstates, and these guys don't break that fact. Okay? Yeah.
Yeah. So partially going back to Matt's question, if I understand how you would implement this in a circuit would be with like rotation gates, like these rotation gates. And so like fault tolerant, that would break down into some number of T gates, and then of course the number of T gates is the number of T gates that gives you your accuracy. So I guess maybe the question, maybe just observation for me to understand, but also like if you have a specific accuracy requirement, doesn't that sort of answer his question? Because the number of T gates you may need 50, 100 T gates, right?
Okay.
Rotations, and so if you count the number of T gates based on the precision of the rotations, then that maybe gets you to a point where you have something that could be just done, could be simulated easily classically.
I see. So I guess I'm trying to see what is the question that I should answer. I only can say that in print, if you are concerned about the T gate.
No, I'm not concerned. I guess I'm trying to connect all the dots in my head. It's like, okay, it seems like to me that the accuracy of the rotations gives you a certain amount of complexity, right, in these
circuits.
Right?
Yes, that's right.
And that sort of answers Matt's question of, are these circuits too simple? If they're very simple, then we can just simulate them classically.
I guess we have different interpretation of his question because
I think he's saying the right question.
Yeah? Okay. Because I thought you were worried that our W's are not doing anything but introducing the phase.
That was a specific subset of worries.
Okay.
That I was able to say.
So we're addressing different parts of your question.
Yes.
Okay. All right. Cool.
But it comes down to if theta can be off by pi over 2, I can always just put it onto a Clifford gate, and then it needs no t's.
Right.
If theta can be only be off by 1 e to the minus 17, and the numbers you optimize to are always very far away from the poles, then it's very hard to synthesize, and you can put this through grid synth, and it'll tell you exactly how many gates you need for theta, and then that would tell you whether how hard it would be, like the complexity of that.
Right.
I think would be
Yeah. So in my mind, it's kind of like the accuracy that you need to. I mean, I'll just say the accuracy you need for these rotations dictates the complexity of the circuits, and therefore.
That's right. Yes. Right. Also, we could, in principle, step from the optimal thetas, or don't put optimal thetas, but put next to optimal values that would reduce the number of T gates, because we always can compensate for non-optimal rotations by just having more configurations, right? So more matrix elements, right? So that's one knob that we, in principle, have at our disposal. Okay. Yeah.
Okay.
Just like maybe to head off the question before, are we going to get a rotation count at the end of this? Like, is there a research estimate that's been done?
Yeah,
It's like the number of rotations that are needed in this?
Mostly C-nodes, yeah, because...
okay, 20 C-nodes because you're doing NISQ. Well, yeah, makes sense. Okay.
NISQ kind of estimations. Right, so one other nice feature is simple encoding here, because in principle, we can split all the orbitals which are doubly or zero occupied and the singly occupied. So that means for the doubly occupied orbitals, we could map orbitals directly to qubits. So that's a factor of 2 reduction of the number of qubits that in principle you need. That's one feature. And one thing before the end, I want to really make a connection to is the error correction codes. Because what these quasi-symmetries allow you to have is the configurations. This is our configurations. Let's say we have orbital seniorities as our quasi-symmetries, right? Some orbitals have orbital seniorities 1, some orbitals have orbital seniorities 0, and that's essentially unpaired electron pair rotations, right? But then in the Jordan-Wigner specifically, right? So our orbital seniority quasi-symmetries are double Z's essentially, right? So they're Pauli products, and there are so essentially n symmetries for the 2n qubits we have, And what this means is that there is a Clifford rotation that will transform all these guys into single Z's. Okay? And so what this means for a state, that we can partition state 50-50. So 1/2 of the state will be a product part, which will enumerate the orbital seniorities, zeros or ones, right? Literally. And another part is entanglement, right? So that part carries all the entanglement that the pair rotations are including, right? So with that, effectively what we have is logical qubits, first half, entangled half, and the syndrome qubits in the product half, right? And our W operators, pair rotations, essentially are logical operations on logical qubits, okay? So that's an interesting connection with the error correction codes. Now, this also allows us to hugely reduce measurements, okay? How do we do that? Because now we have this partitioning that we can also put on Hamiltonian. Hamiltonian is linear combination of Paulis. And now all the Paulis could be split again, 50-50. Inside each Pauli, this will be the classical part where they correspond to the product part of the state, right? And this is quantum corresponding to the entangled part of the state. And what we do when we do measurement of matrix elements, we first pre-compute the classical part. So we do this on a classical computer, right? So this classical part with the product states of Brian Ket, right? So this is just a number that can be calculated, and lots of these numbers are zeros. Why? Because if you think about the part of P, let's say for a single qubit, if it's X, but these Z parts are 0, 0, or it's 1, 0, and this part is Z, so they will get you zeros very quickly, right? So like more than 90% of all the matrix elements, of all Paulis, kind of just get canceled when we do this pre-computing. Essentially, that is the echo of the stuff that I was talking before. After like we were thinking about that part of the Hamiltonian connects the different seniority sectors and part doesn't connect them, right? So this is in the qubit language the efficient way of accounting for that, right? And then once we find this partly integrated the product part Hamiltonian, we calculate matrix element only on the logical qubit side, right? And so that essentially done by extended swap test. That's this technique that you, well, many of you know. So we can in principle also put some variance reduction techniques, but we haven't done it yet. So the results are pretty good even before putting any variance reduction. So should I just try to wrap up?
I think we should try to wrap up.
Okay, good. So yeah, so then I guess these are the results for N2 and H2O. Those systems, when you stretch, they're difficult, and this is the errors. The gray lines are chemical accuracy. So these are classical methods that break down, and Q-sense in two versions, which are slightly different optimization techniques. They allow us to be below the chemical accuracy. Small basis, oops, wrong step. I will not talk about this. The important part is that we, with the kind of these molecules, the main concern for us was the number of C-nodes, right? And so the maximum, of course, it deviates from different state to different state. The maximum number of C-nodes we have for the nitrogens, let's say 261. So I believe, or at least 63 C-nodes probably we could, or 100 C-nodes we can afford at the IBM machine these days, right? 260 probably, yeah, we will need to trade for more matrix elements, right? So unless we are doing really aggressive mitigation. But in the near future, I feel like these are, well, reasonable numbers to be able to do, right? And this is another aspect, measurements. We're comparing with the VQE measurements. It's in millions to achieve the chemical accuracy. All the matrix elements calculated for different methods, right? They are lower than the VQE numbers, and still reasonable, because if this is in the millions, I assume that superconducting architecture can do one measurement in 10 microseconds, and so 1 million would be, oh yes, 10 seconds or about a minute. So this in millions is completely doable. Okay, and all matrix elements are together. They're still lower than the 1 VQE cycle. So we were very happy with this result. Okay, new quasi-symmetries. This is just an idea that okay, if we go to the compounds like this, seniorities may not be the best, but there are other chemically intuitive symmetries like d orbital numbers or local spins. And we're also thinking about algebraic search, just looking at the potential operators that contain only few modes, right? And they almost commute with the Hamiltonian, right? So the cost function to select those symmetries will contain commutators with the Hamiltonian, right? And trying to minimize that sort of operators' cost functions, right? This summary, so we believe in the balance between essentially having more stuff done on a quantum versus less stuff done on a quantum, so putting more on a classical, right? So that's one of the key things to usefulness in the near term and maybe early fault tolerant. We developed these ideas based on the quasi-symmetries that allow us to split the big Hilbert space and split the load more efficiently. I think we kind of came up with a quantum version of Slater-Condon rules because now we need matrix elements between the quantum configurations, right, and not just Slater determinants. We could use more quasi-symmetries for essentially characterizing. This is one of the, I guess, answer to the questions in the questionnaire, what are the main challenges these days? I believe it would be nice to have practical Hamiltonian complexity theory, meaning that, okay, if I have a molecule, how complicated the Hamiltonian is for DMRG method or for some other classical methods, right? And I believe that maybe quasi-symmetries could be a step in the right direction, sort of the Hamiltonians that contain more or commute more efficiently with some local operators. They are simpler to treat with, say, couple cluster method, right? And yeah, cousins can be also used for state preparation, excited states, and what is another interesting feature is that because we're diagonalizing matrix, we're not trying to lower energy. We could use it for non-Hermitian Hamiltonians too. Okay. So with that, let me thank people who did the work, my group, and some funding support, and all of you, of course, for your kind and patient attention. Yeah.